In this lecture, we are going to explore how to find the electric field due to uniformly charged ring. Again, I repeat, how to find the electric field due to uniformly charged ring. Okay, so you can note the heading electric field due to uniformly charged ring. Okay, so take care of one thing. We have to focus on the approach of the derivation. Because see, uniformly charged ring means the charge density is same at each point. The charge density will be the same at each point of the ring. Now there can also be cases when the charge density will vary on the ring. But the approach of the derivation will be the same. Of course, the end formula will differ. The approach of derivation will be the same. So be careful about the steps of the derivation, number one. Number two, the case of electric field due to a uniformly charged ring is very frequently used formula. So in this case, whatever will be the end formula, we will have it on fingertip for frequent applications in MCQs or the numerical problems. Okay. So the formula for the uniformly charged ring, we must have as a fingertip formula. Now suppose we have a uniformly charged ring. Say we have a ring with a charge Q and say radius R. Okay. And say there is a point P on the axis of the ring. This is the axis of ring. Axis means a line perpendicular to the plane of the ring and passing through its center. A line perpendicular to the plane of the ring and passing through its center. And there is a target point P on the axis. And so the distance of P from the center, the distance of P from the center is Z. Now I'm taking the coordinate axis, coordinate system. So suppose this ring is lying in the XY plane. And this is the Z axis, okay? Say this is X axis, this is Y axis, and this is Z axis. And we have to find the electric field at a point P. Got it? Now we know how to find the electric field due to an extended object. We have to apply the method of calculus. We will take a charge element dq. We will take a charge element dq, step 1. Step 2, we will find the infinitesimal field dE because of this dq. And step 3, we will integrate dE to find the total field. So suppose I'm taking a charge element. I'm taking an element on the ring like this. This is an element on the ring. Say we ran a linear variable L with this dl. This angle is say phi and this angle is d phi. So if you see the top view, be clear about your angles and the plane of lines. If you see the top view, you will have something like this. This is a ring, okay? And this is your x-axis, this is y-axis, and z-axis is coming out of the plane of the paper. So we'll denote the z-axis like this. And this is the element of the ring whose linear coordinate is L, linear width is dl. The angular coordinate, which is called the azimuthal angle, is phi. This is also called the azimuthal angle or the azimuth. And the angular width is d phi, okay? And say the charge on this element is dq. So let dE1 be the electric field due to this element, okay? So if you want to make the electric field because of this element dq at P, This is your dq, and you have to make the field because of this element. The first step will be make a line joining the target point with the source. So this is the line joining the target point with the source, and the electric field vector will be outward along this line. The field vector will be outward along this line. So let this vector be dE1. Okay. Now what will be this distance? This is the radius r. So this will be z square plus r square under root. Correct? So your dE1 will have a magnitude Coulomb's constant, the source dq divided by r square plus z square root square. So it will be simply r square plus z square. This will be the value of dE1. Okay, this is the value of dE1, the electric field because of the charge element dq. Now let the line, say this element has a position which I am giving a name A. So let the line AP subtends an angle theta with the plane of the ring. Let the line AP subtends an angle theta with the plane of the ring. And what is the plane of the ring? XY plane. So let the line AP subtends or makes an angle theta with plane of ring. That is which plane? XY plane. Got it? So if you see in this figure, what will be the angle theta? So I'll say this will be the angle. Let me change the color for more clarity. Say we are using this pink color. This angle above the plane of the ring till the line AP. This angle is theta. Okay, if you want to see the side view, if I'm making the side view for clarity, so suppose I'm representing the plane of the ring as a horizontal line. This is the plane of ring, that is XY plane, and this is your Z axis, and this is a point P at a distance of Z, and this is the element A, correct? And so your angle theta, this is a vector dE1, and this is your angle theta, and this is what R, this is Z square plus R square. So if you see the side view, you'll see something like this. This is the XY plane in which the ring is lying, which in 3D case would look something like this. Okay. This is the target point where we made the vector dE1. This is angle theta, and this is the center of the ring. Okay. Now see, now dE1, we have to take the components, because when you integrate, when you need to find the total field at P, it will be the summation of all D. So it will be the summation of all dE1 because of different elements, correct? Now, since it is a vector summation, the vector integral, so we have to take the components. Remember, whenever you are integrating a vector quantity, it cannot be simply integrated. We have to resolve them along different axes. So if you see here, if I'm taking a horizontal plane, something like this, this is your XY plane, correct? This is a plane parallel to the plane of the ring. This is a plane parallel to the plane of the ring. If this angle is theta, this angle will also be theta. So we can resolve D into component. One will come to be dE1 cos theta. right? This is your xy component. I'm not saying this is x component or y component. This is the component in the horizontal plane, dE1 cos theta. And this component will be dE1 sin theta. Same approach will be applicable in the problem which we'll be doing in the coming lecture, when your lambda will depends on the azimuthal angle phi. Lambda will vary with phi. Everything approach will be the same. Now see, if you want to indicate the two components d1 sin theta, which is along the z-axis going upward. d1 sin theta is along the z-axis going upward, and de1 cos theta is in the xy plane. Is in the xy plane. So if you want to represent these component in the top view figure, so you will have along this line, you will have a component dE1 cos theta, correct? dE1 cos theta. And one component will be along the z-axis, which I am denoting as a dot, dE1 sin theta, correct? Now you can further resolve. If in this figure you want to make, you will see the component like this. If this angle is theta, this will be theta, this will be dE1 cos theta, and this will be dE1 sin theta in the side view. Now dE1 cos theta is the xy component. dE1 cos theta is the xy component. If this angle is phi, this angle will also be phi, vertically opposite angle. So we have to further take the components of dE1 cos theta on the x-axis and y-axis. Clear? When you are integrating, we have to integrate on the three axes. So we have to further take the components of dE1 cos theta on the x-axis and y-axis, and then we can integrate on the three different axes. But in this case, in this particular case, when the ring is uniformly charged, we can take advantage of symmetry. We can take advantage of symmetry and reduce some of the steps of integral. But this advantage can only be taken when the ring is uniformly charged. Then only symmetry will be present, okay? So suppose we are taking one more element which is diametrically opposite to this dq. First of all, you note all this figure. You can make the video still and note down all the figures and understand everything, okay? And then we'll go to taking another symmetric element opposite to this dq, okay? So suppose suppose I'm taking one more element opposite to this dq, diametrically opposite to dq, say dq dash, okay, which is diametrically opposite, and we want to make the electric field because of this element at a point P. So again, we have to join point P, which dq dash, and it will make the electric field away from it, say dE2, okay, dE2. Now what will be the magnitude of dE2? So dE2 will be C dq dash divided by r square plus z square, correct? So this is your dE2. Now, since both charges can be written, both length are equal and at both the location lambda is same, so dq will be lambda dl and dq dash will again be lambda dl. So we can write dq is equal to dq dash. So therefore dE1 is equal to dE2. Okay, so both the electric field have the same magnitude. Now this is something which is beneficial for us. Now if you take its component dE2, so it will give you the component in the similar way, one in the xy plane dE2 cos theta and one along the z axis dE2 sin theta. Got it? This is the second figure I made for clarity. In that figure, I have shown one element. In this figure, we are indicating two symmetrically located elements so that both are giving the component dE1 and dE2 cos theta in the xy plane. And along the z axis, both the components are upward, dE1 sin theta and dE2 sin theta. Okay, if you make in this figure, so say the symmetrically located element is at B. So we can make a line joining B with P. So it will make an electric field something like this. This will be your dE2. If you take the component, this will come to be dE2 cos theta, and this will come to be dE2 sin theta. Got it? If you see in this figure, if you want to indicate the same symmetrically located element in this figure, this is your dq dash. So it will give you a component dE2 sin theta, and here it will give you dE2 cos theta, correct? Now see, in the xy plane, we have two components which are opposite to each other, dE1 cos theta and dE2 cos theta. And we have seen dE1 is equal to dE2, dE1 is equal to dE2. So what will be the net field component in the xy plane? So you can write dE1 cos theta minus dE2 cos theta. The answer will be 0. There will be no component in the xy plane. So therefore the net field in the xy plane will be integral of dExy. So answer will be 0. No field in the xy plane. See, I have done all the steps because I told you same steps will be applicable when lambda is variable. In that case, it is possible that we may not be able to take the symmetric advantage. So in that case, what we have to do, we have to take the component of dE1 cos theta along the x and y axis. In this case, we can go away without taking further components on x and y axis, because in the xy plane, we are able to find a symmetric opposite element of the field which is getting cancelled away, dE1 cos theta, dE1 cos theta. Got it? Now what will be the both dE1 and dE2 are equal in magnitude, so I can write twice of dE1 sin theta. So I'll get twice of, and what is your dE1? The value of dE1 we can take from C dq r square plus z square. C dq r square plus z square sine theta. Now let's see what are the quantities which can be brought out of the integral. So r is a constant, the radius of the ring, as you are changing the element, r is not changing. Correct? Z is constant, the perpendicular distance of the target point from the center of the ring, it is not changing. Theta is constant, the inclination of the line joining the element with the target point with the plane of the ring. Theta is what? The inclination of the line joining the target point with the element with the plane of the ring. So for each element, this inclination is same. So theta is also constant. And dq, we can write lambda times dl. So lambda can be taken out also because lambda is also constant. Right now we are talking about a uniformly charged ring. In case of a non-uniform charged ring, lambda may not be taken out of the integral. So I'll get 2c lambda sine theta divided by r square plus z square under root integral of dl. Now we have to put the limit of L. Now you can see we ran L from this point. So L will be 0 here, L will be pi r here, as we have seen in the skill of running a linear variable, and L will be 2 pi r once you complete the whole ring. But since we are taking two elements together, mind it, since we are taking two elements together, we need not to integrate the complete ring. We will be integrating half of the ring, because when you will be integrating half of the ring, the rest half will be taken care of itself. So we will put the value of limits of L from 0 to pi r. So Ez will come to be 2c lambda, put the value of sine theta. So you'll see the right angle triangle. Sine theta will be perpendicular by hypotenuse. That means z by z square plus r square. Z by r square plus z square. Sorry, that was square in the value of magnitude of the electric field. This is a square, okay? Distance square. So I forgot to put the square, or you can remove the radical sign. Z by r square plus z square, and this will be L within the limits 0 to pi r. So we'll get Ez is 2c lambda z by r square plus z square 3 by 2 pi r. This is the final answer for Ez. Now put the value of lambda, since it is uniformly charged ring, you can put lambda is equal to q by 2 pi r. So Ez will come to be 2c mod of q by 2 pi r z pi r by r square plus z square 3 by 2. So 2 pi r 2 get cancelled away, and Ez came to be cqz by r square plus z square 3 by 2. This is Ez. And since there is no Ex and Ey, so you can write E is equal to Ez square plus Exy square. Now Exy is 0, so it will be simply E modulus of Ez. So the net electric field will be CQ Z. C is the Coulomb's constant, R square plus Z square 3 by 2. This is the final derived formula for the electric field on the axis of a uniformly charged ring. CQZ by R square plus Z square 3 by 2. Okay. Now, as I told you, this formula will be used in many of the numerical, many of the secondary applications. So we will have it on fingertip. We will have it on fingertip. If there is a ring of charge Q, and of course we are talking about uniformly charged, and the radius is R, and there is a target point P at a distance of Z. So the electric field will be away from the ring. Electric field will be away from the ring if the ring is positive. If the ring is positive, okay? And the electric field will be towards the ring. Electric field will be towards the ring. The ring has negative charge. So the field will be like this, towards the center. And the field will have a magnitude C, Q, Z. Z is the distance of the point from the center. R square plus Z square 3/2, like this. Okay. So this is the end point, the fingertip point. When you are not sure about the sign of the charge, you can take the positive charge model, as we always do. When you are not sure about the sign of the charge, you can take the positive charge model. But if you're taking a positive charge model, make sure do not put the modulus sign. So in this case, you can write C Q Z by R square plus Z square by index 3/2. Got it? So this is the value of the electric field on the axis of the uniformly charged ring. Got it? Now, in the second lecture of this, we will see some of the points, how to plot the graph of E versus Z, how to plot the graph of E versus Z, and we will see what will be the value of Z, where the field will be maximum. For that, we will use the concept of maxima minima. We will differentiate E with respect to Z, and you will see when you use maxima minima, so you'll get dE by dZ will come to be 0, and we will see next lecture with complete working. When we will apply this thing and do the differentiation, Z will come to be plus minus R by root 2. So this is the value where the field will have a maximum magnitude. Okay. So this is the derivation of the formula for electric field on the axis of a uniformly charged ring. And pay care for the steps of the derivation, because same steps will be applicable when the ring is non-uniformly charged. Okay.